Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the Tharsis Bulge. Volcanoes that can change a planet's spin. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet. The universe is vast, and we are ready to explore. This region, located on Mars, is an extraordinary geological feature that spans approximately 4,000 kilometers in diameter. It is home to some of the largest volcanoes in the solar system, including Olympus Mons, which towers over 25 kilometers high, dwarfing Earth's highest peak. The Tharsis Bulge encompasses a network of volcanic structures that provide invaluable insight into the planet's geological history and evolution. Distinctive in its formation, this area is believed to have been created by the upwelling of magma from the planet's interior, leading to extensive volcanic activity over millions of years. The sheer size and scale of these volcanoes suggest a different tectonic process compared to Earth. Rather than moving plates, Mars exhibits a more static crust, allowing these colossal formations to grow without interruption. Significance lies not only in the sheer size of the Tharsis Bulge, but also in its impact on the Martian atmosphere and climate. The eruptions from these volcanoes may have released vast amounts of gases, contributing to changes in surface conditions. Understanding these processes is crucial for grasping the historical climate of Mars and its potential for habitability. The Tharsis Bulge remains a focal point for scientists studying planetary geology, offering clues about volcanic activity and its broader implications for planetary dynamics. Insights gained here extend beyond Mars, influencing our understanding of similar features in other celestial bodies. The geological formation of the Tharsis Bulge reveals a complex history that spans billions of years. This region is dominated by an array of colossal volcanoes, including Olympus Mons, which stands as the tallest planetary mountain in the solar system. The origins of this impressive bulge can be traced back to a combination of tectonic and volcanic processes that began during the early history of Mars. It is believed that the initial formation was driven by mantle plumes, hot columns of molten rock rising from the planet's interior. As these plumes reached the surface, they generated immense volcanic activity. Over time, repeated eruptions contributed to the gradual buildup of massive lava flows, creating the prominent shield volcanoes that characterize the landscape. This volcanic activity not only shaped the surface, but also influenced the planet's lithosphere, leading to subsurface changes that affected its tectonic features. The unique characteristics of the Tharsis Bulge include its extensive rift systems, which indicate periods of tectonic stretching and fracturing. These rifts are evidence of the ongoing geological processes that continue to shape the Martian surface. Analysis of the stratigraphy in the region provides valuable insights into the timing and frequency of volcanic eruptions, contributing to a deeper understanding of the planet's evolutionary history and its geological resilience. The Tharsis region, an expansive volcanic plateau on Mars, stretches approximately 4,000 kilometers across the planet's surface. This area stands elevated, rising several kilometers above the surrounding plains. Enormous shield volcanoes, including Olympus Mons, dominate the landscape. The sheer size of these formations is staggering, with Olympus Mons reaching about 22 kilometers in height, making it the tallest volcano in the solar system. The terrain exhibits a variety of geological features, including deep canyons and vast lava flows, which reveal the dynamic history of volcanic activity. These structures indicate periods of intense geological upheaval, potentially influencing the planet's atmospheric conditions. Geological mapping shows a complex interplay of volcanic and tectonic processes. The presence of calderas, formed by the collapse of volcanic edifices, suggests a prolonged history of eruptions. Some of these calderas span over 100 kilometers in diameter. The Tharsis region's unique geography is also characterized by a network of fissures, hinting at the underlying tectonic activity that may have contributed to the region's formation. Analysis of these features allows for a deeper understanding of how volcanic processes can influence planetary dynamics. This knowledge is crucial in deciphering the history of Mars and its potential for hosting life, both past and present. The interplay of geological forces continues to shape this remarkable landscape. The tectonic framework of Mars reveals a planet shaped by both volcanic activity and crustal dynamics. This region, dominated by the Tharsis Bulge, is a prime example of how geological processes converge to influence planetary characteristics. It is home to some of the largest shield volcanoes in the solar system, including Olympus Mons, which towers over the surrounding plains. Their immense size suggests a long history of volcanic activity, sustained by a unique tectonic environment. In contrast to Earth, Mars exhibits a relatively static crust, with limited plate tectonics. The Tharsis Bulge, while primarily volcanic, impacts the underlying lithosphere, contributing to a series of structural deformations. These changes can be seen in the form of rift valleys and fault lines that radiate outward, indicating the intense stresses exerted by the massive edifices. The gravitational pull of the bulge influences the planet's rotation, creating subtle variations in spin and tilt. These shifts play a significant role in climate dynamics and atmospheric conditions over geological timescales. The presence of the bulge essentially serves as a stabilizing force, affecting seasonal patterns and potentially influencing the distribution of ice and dust across the Martian surface. This intricate interplay between volcanic activity and tectonic stability defines the unique geological narrative of Mars. Volcanic activity on Mars reveals stark contrasts when compared to Earth. The Martian surface showcases colossal shield volcanoes, such as Olympus Mons, towering significantly higher than any terrestrial counterpart. Their gentle slopes and expansive bases indicate a prolonged eruption style, characterized by the release of low-viscosity lava. This differs from Earth's fiery stratovolcanoes, which erupt explosively due to higher viscosity magma. Such variations highlight the influence of atmospheric pressure and temperature on volcanic processes across the two planets. The absence of plate tectonics on Mars allows these volcanoes to form over extended periods, resulting in structures that grow larger without being disrupted by shifting tectonic plates. These massive edifices stand as silent witnesses to billions of years of geological history, capturing the planet's volcanic timeline in their layers. On Earth, volcanic activity is often accompanied by seismic events, as tectonic movements trigger eruptions. Conversely, the relative geological quiescence of Mars suggests a more stable environment in which volcanic activity is isolated from seismic disturbances. The distinct characteristics of Martian volcanism, combined with its unique atmospheric conditions, lead to a different evolutionary path for the planet's surface. This divergence provides vital insights into the broader dynamics of planetary formation and activity within our solar system. The Tharsis Bulge hosts 4 major volcanoes, each a testament to the geological activity that has shaped Mars over millions of years. Ascraeus Mons A4, the most prominent, towers approximately 22 kilometers above the surrounding plains. Its extensive summit caldera suggests a history of explosive eruptions, leaving behind a complex structure that hints at both violent and effusive volcanic events. To the northwest lies Pavonis Mons, notable for its broad, gently sloping profile. This volcano stands as a giant among its peers, with a height exceeding 13 kilometers. The features observed indicate a more sustained period of volcanic activity, characterized by the flow of lava across vast distances. The gently descending flanks of Pavonis reveal a calm that belies the potential for significant geological upheaval. Further north, Arsia Mons emerges as a unique structure, marked by a distinctive steepness and an expansive caldera. The geological records suggest a history of varied eruption styles, providing clues to the internal processes driving volcanic activity. Finally, the lesser-known Tharsis volcano, Olympus Mons, dwarfs its siblings, reaching a staggering height of 25 kilometers. Its sheer scale and the extensive shield formation signify a long history of intermittent eruptions, allowing it to dominate this region. The interplay of these volcanoes continues to shape the understanding of Martian geology. The largest volcano in the solar system, Olympus Mons, rises approximately 22 kilometers above the Martian surface, dwarfing its terrestrial counterparts. This colossal shield volcano, with a diameter of nearly 600 kilometers, presents a unique profile characterized by gentle slopes and a vast caldera at its summit. The sheer scale of this geological feature prompts inquiries into its formation and the processes that have shaped its evolution. Surrounding the base, expansive lava flows extend outward, evidence of extensive volcanic activity that persisted for millions of years. The smooth plains, interspersed with fissures and cracks, indicate a history of effusive eruptions, where fluid basaltic lava spread across the landscape. These characteristics suggest a relatively low viscosity magma, enabling the formation of such a massive structure without the violent explosive events typically associated with volcanoes on Earth. The caldera itself, measuring over 80 kilometers wide, comprises multiple overlapping craters, hinting at successive eruptive phases. This region exhibited features that provide insights into the thermal history of Mars, as well as its volcanic timeline. The absence of significant erosion highlights the planet's thin atmosphere and the longevity of volcanic activity. The study of Olympus Mons not only contributes to the understanding of volcanic processes, but also offers broader implications for the geological history of Mars as a whole. Ascraeus Mons stands as one of the 3 prominent volcanoes within the Tharsis region, characterized by its massive shield structure. This volcano has a complex history of eruptions, marked by various phases of activity. Features such as large lava flows and extensive ash deposits indicate a period of significant volcanic activity that likely occurred over millions of years. The earliest eruptions may have been effusive, resulting in the formation of broad, gently sloping layers of basalt. As volcanic activity evolved, it transitioned to more explosive eruptions, producing pyroclastic materials that spread across surrounding plains. Evidence suggests that these eruptions may have contributed to the alteration of the Martian atmosphere, releasing gases that could have influenced surface conditions. Geological formations, including summit calderas and radial fissures, further illustrate the dynamic processes that have shaped Ascraeus Mons. Analysis of the stratigraphy reveals a timeline of eruptions, suggesting periods of dormancy and resurgence. Some of these eruptions were likely contemporaneous with climatic changes on Mars, hinting at a relationship between volcanic activity and the planet's evolving environment. Currently, Ascraeus Mons remains dormant, yet its history offers insights into the potential for future volcanic activity, serving as a reminder of the dynamic nature of this region and its capacity for change over geological time. Apavanus Mons, one of the largest volcanoes within the Tharsis region, showcases a unique geological profile characterized by its gently sloping flanks and expansive caldera. The structure spans approximately 450 kilometers in diameter, presenting an impressive elevation of nearly 14 kilometers above the Martian surface. The smooth slopes suggest a history of effusive eruptions, where lava flowed steadily, contributing to its broad, geode-like form. Evidence of past eruptions can be observed in the layered deposits surrounding the summit. These layers indicate a series of volcanic events, each contributing to the growth of this colossal edifice. The presence of fissures and radial fractures on the surface hints at the complex plumbing system beneath, which may have facilitated the transport of magma to the surface. These geological features reflect the interplay between volcanic activity and the planet's tectonic processes, revealing a dynamic history that extends over millions of years. Sedimentary deposits, likely formed by interactions with water, can also be found near the base of Apavanus Mons. This suggests that past climatic conditions may have allowed for liquid water to exist, influencing the geological evolution of the region. The study of eruption patterns provides crucial insights into the longevity and potential reactivation of these volcanoes, underscoring the intricate relationship between volcanic activity and planetary change. Tharsis Mons stands as one of the most imposing features within the Tharsis Bulge, its colossal shield shape dominating the Martian landscape. At an elevation of approximately 22 kilometers, it is taller than any peak on Earth. This immense structure offers a unique opportunity to study the geological processes that shaped it. The slopes, gently inclined and layered, suggest a history of frequent lava flows, each contributing to its current form. Surface analysis reveals distinct characteristics, including a lack of significant erosion, indicating that the region has remained relatively stable over extensive periods. The caldera at its summit, measuring nearly 120 kilometers across, hints at multiple eruptive phases and possible collapse events. These features provide valuable clues about the thermal and magmatic history of this region. The presence of large fissures radiating from the caldera signifies intense volcanic activity in the past, while the surrounding plains are littered with volcanic debris, revealing the expansive reach of past eruptions. These remnants suggest that Tharsis Mons has played a significant role in influencing the atmospheric conditions of Mars, potentially affecting its climate cycles. The study of such formations enables scientists to better understand not only the history of Mars, but also the broader implications of volcanic activity on planetary evolution as it shapes environmental dynamics over time. The flows of lava that have carved this landscape reveal a history of immense geological activity. These ancient channels, once teeming with molten rock, have solidified into a series of intricate pathways, each telling a story of the forces that shaped them. The surface exhibits a variety of textures, from smooth, glassy areas to rugged terrains, indicating varying temperatures and cooling rates during the eruptions. These formations have implications beyond mere aesthetics. The way lava interacts with the Martian crust can alter topographical features, influencing regional gravity and even the planet's axial tilt. Some flows have contributed to the emergence of vast plains, while others have formed towering cliffs, creating a diverse environment that may have once supported transient water bodies. Fluids that once coursed through these channels have since vanished, leaving behind a stark reminder of a more active past. The remnants of these flows provide insights into the thermal history of Mars, revealing how volcanic activity may have cycled through periods of dormancy and eruptions. Each layer of lava holds clues to the conditions existing at the time of its formation. In the context of planetary evolution, the role of these lava flows extends far beyond Mars, offering valuable parallels to other celestial bodies, where volcanic activity has also played a crucial role in shaping their landscapes. These caldera structures represent the remnants of immense volcanic activity, indicative of a complex history. Formed through the collapse of the ground following explosive eruptions, they reveal the tremendous forces at play beneath the surface. Each caldera, with its distinctive shape and depth, provides insight into the volcanic processes that shaped this region. The largest of these calderas, Olympus Mons, measures approximately 630 kilometers across, dwarfing any terrestrial formation. Its sheer scale suggests a prolonged period of volcanic activity, allowing for the accumulation of vast amounts of material over time. Such formations are characterized by steep walls, often exhibiting terraced features that reveal successive stages of eruptions and collapses. Surrounding calderas, smaller in scale yet equally fascinating, exhibit diverse morphologies, hinting at the variability in eruption styles and volcanic composition. Some display smooth, gently sloping interiors, while others are marked by rugged terrain, suggesting explosive events that contributed to their formation. In comparison, many terrestrial calderas showcase similar characteristics, underscoring the universal nature of these geological processes. The study of these structures not only enhances understanding of Mars's geological history, but also provides a framework for investigating volcanic activity across different planetary bodies within the solar system. The age of the Tharsis volcanoes reveals a complex timeline of volcanic activity, stretching back billions of years. Initial eruptions likely began during the Noachian period, characterized by a wet and dynamic landscape. This region experienced a substantial phase of volcanism, with extensive lava flows reshaping the surface. The transition into the Hesperian period marks a significant shift as the intensity and frequency of eruptions waned, leading to a more subdued volcanic landscape. Analysis of these structures indicates that the most prominent volcanoes, such as Olympus Mons, have experienced multiple eruption episodes, each contributing to their immense size and unique morphology. Eruptions varied in scale and style, with some producing vast, smooth lava plains, while others resulted in explosive activities that scattered ash and volcanic debris across the Martian surface. The distinct layers visible in their edifices signify a history of repeated activity, interspersed with periods of dormancy. Evidence suggests that these volcanoes may still hold geothermal energy beneath their surfaces, hinting at the possibility of future eruptions. Understanding this eruption history not only informs knowledge about Tharsis, but also aids in comparative planetology, offering insights into the volcanic processes that shape other planetary bodies in the solar system, such as Venus and certain moons of Jupiter and Saturn. The geological features of the Tharsis region have left an indelible mark on the climate of Mars. Elevated by more than 10 kilometers, the Tharsis Bulge influences atmospheric circulation patterns, contributing to a significant alteration in thermal dynamics across the planet. These towering volcanoes, with their vast calderas and extensive lava flows, once released substantial quantities of gases, including water vapor and carbon dioxide, into the Martian atmosphere. The release of such gases would have contributed to a greenhouse effect, potentially warming the surface and enabling liquid water to exist for extended periods. Evidence suggests that this volcanic activity was not merely localized, but had far-reaching implications for the Martian climate over millions of years. The interplay between volcanic eruptions and climate change may have facilitated periods of greater habitability, supporting the possibility of ancient microbial life. As the eruptions waned, the cooling of the planet likely led to a more arid environment, reshaping the landscape into the cold, dry conditions observed today. This historical perspective reveals a planet whose climate was once dynamic and responsive to geological forces. Tharsis remains a crucial piece of the puzzle in understanding how volcanic activities can influence not just a planet's surface features, but also its atmosphere, climate, and potential for life over geological timescales. The Tharsis Bulge, a colossal volcanic region on Mars, plays a significant role in shaping the planet's atmospheric evolution. Towering volcanoes, such as Olympus Mons, represent not just geological wonders, but also indicators of historical atmospheric conditions. Their eruptions may have released significant volumes of gases, including carbon dioxide and sulfur dioxide, into the thin Martian atmosphere, contributing to the greenhouse effect in its formative years. This process likely facilitated a warmer, wetter environment, suitable for liquid water to exist on the surface. The gradual cooling and subsequent geological inactivity led to a decline in volcanic activity, resulting in a thinning of the atmosphere. Such changes profoundly influenced surface conditions, leading to the arid landscape observed today. The interplay between volcanic activity and atmospheric composition reveals a dynamic relationship. Eruptions can inject particulates that reflect sunlight, temporarily cooling the planet, while the release of greenhouse gases can enhance warming. These interactions demonstrate the delicate balance that governs Martian climate and its evolution over millions of years. Investigations into the Tharsis Bulge also provide insights into the potential for past life. The environmental shifts induced by volcanic activities create a framework for understanding habitability, emphasizing the need to study these features further in the quest to unlock the planet's secrets. Volcanic gases serve as crucial components in the Martian atmosphere, influencing its composition and climate. Emissions of carbon dioxide, sulfur dioxide, and water vapor from volcanic eruptions contribute to the planet's greenhouse effect, albeit on a much lesser scale than that of Earth. These gases, once released, interact with the thin Martian air, altering pressure and temperature conditions within this region. The presence of carbon dioxide in particular plays a significant role in the seasonal changes observed on Mars. During warmer periods, the gas can sublimate from polar ice caps into the atmosphere, increasing density and potentially affecting wind patterns. This interaction establishes a feedback loop that may influence weather phenomena and surface processes across the planet. Additionally, volcanism introduces unique chemical compounds that can react with the existing Martian atmosphere, resulting in the formation of clouds and dust storms. These storms can envelop vast areas, redistributing materials and impacting surface visibility. Furthermore, the interaction between volcanic gases and Martian soil can lead to the alteration of minerals, highlighting the dynamic processes at play within the planet's crust. Studying these volcanic gases provides insights into the geological history of Mars and its atmospheric evolution, revealing the intricate relationship between volcanic activity and climate dynamics. Understanding these interactions is essential for comprehending the potential for life and future exploration on this intriguing planet.
Tharsis volcanoes exert a profound influence on the distribution and dynamics of surface water on Mars. Their immense mass alters the planet's gravitational field, leading to localized changes in hydrological patterns. This region, characterized by its towering shield volcanoes, creates thermal anomalies that can affect atmospheric conditions, thereby influencing evaporation and precipitation cycles. The sheer scale of these formations, which includes Olympus Mons, the tallest volcano in the solar system, suggests that they may have played a significant role in ancient Martian climate. During periods of increased volcanic activity, the release of gases, such as water vapor and carbon dioxide, could have contributed to a greenhouse effect. Such an environment may have allowed liquid water to persist longer on the surface, facilitating the conditions necessary for the development of life.
Presently,
evidence of ancient river valleys and lake beds continues to hint at a time when this region was not merely a barren landscape. The remnants of this water cycle are etched into the Martian surface, revealing a complex history of climatic changes influenced by volcanic activity. The interplay between these geological features and the availability of water underscores the dynamic nature of Mars, suggesting that it was once a more hospitable environment than it is today. Geochemical analysis reveals the Tharsis Bulge as a remarkable region, characterized by its extensive volcanic activity. This volcanic province features numerous large shield volcanoes, with Olympus Mons, the tallest volcano in the solar system, standing at a staggering height of approximately 25 kilometers. The composition of the surface materials indicates a predominance of basaltic rock, formed through the cooling and solidification of lava flows. The presence of these basaltic formations hints at a history rich in volcanic outgassing, leading to a significant contribution of gases to the Martian atmosphere. This phenomenon is critical for understanding the planet's thermal evolution. Various studies have detected elevated concentrations of sulfur, chlorine, and other volatiles within the Tharsis region, suggesting a complex interplay between volcanic processes and the planet's hydrological cycle. The Tharsis Bulge also displays signs of past tectonic activity. Fractures and rifts indicate the movement of the Martian crust, possibly influenced by the immense weight of the volcanic structures. This weight may have contributed to the redistribution of the planet's mass, affecting its rotation over geological timescales. Understanding the geochemical composition of this area provides insights into the planet's history and evolution, revealing a dynamic environment that may have once supported conditions conducive to life. The ongoing study of these geological features continues to shed light on the processes that shaped Mars. The influence of Tharsis extends beyond its impressive topography, affecting Martian magnetic field dynamics in profound ways. This colossal volcanic region, characterized by extensive shield volcanoes, alters the planet's internal structure and thermal dynamics. As these immense formations arose, they produced significant heat, which is believed to have contributed to the geological activity deep within the Martian crust. This thermal output impacts the behavior of molten iron in the planet's core, influencing the generation of magnetic fields. The lack of a substantial global magnetic field on Mars contrasts sharply with that of other terrestrial planets. Some scientists propose that the Tharsis region may have played a crucial role in this disparity, as the volcanic activity could have disrupted the planet's magnetic field generation processes. Localized magnetic anomalies are observed in proximity to Tharsis, hinting at the complex interactions between its geology and magnetic properties. These anomalies suggest that remnants of an ancient, more vibrant magnetic field may still be detectable, offering clues about the Martian environment during a time when it may have harbored conditions suitable for life. Understanding the relationship between Tharsis and magnetic field dynamics is essential for reconstructing Mars' atmospheric history. Insights gained from this region inform theories regarding climate evolution and the ultimate transformation of a once potentially habitable world into its present state. Understanding Tharsis's role in Mars's axial tilt reveals the intricate interplay between geological features and planetary dynamics. The vast volcanic plateau, home to some of the largest volcanoes in the solar system, exerts significant gravitational influence on the planet's distribution of mass. This uneven mass distribution affects the axial tilt, or obliquity, of Mars, contributing to its climate variations over time. The elevation of these volcanic structures, with Olympus Mons towering approximately 25 kilometers, alters the gravitational pull experienced across the surface. Such variations can initiate shifts in the rotational axis, leading to changes in climate and atmospheric conditions. These fluctuations are pivotal in understanding historical periods of glaciation and the potential for liquid water to exist on the Martian surface. Research indicates that the Tharsis region may have undergone periods of tectonic activity that further influenced axial tilt. As volcanic activity wanes, the redistribution of mass could lead to a gradual stabilization of the planet's rotation. This stabilization has implications for the long-term climate, affecting the potential for sustaining life. The interplay between volcanic activity and axial tilt continues to be a focal point in planetary science, offering insights into the evolutionary history of Mars. Ongoing studies aim to unravel the complexities of this relationship, shedding light on the planet's past and potential for future exploration.
The unique geological features of the Tharsis region exert a notable influence on Martian seasons, elevated terrain, and the presence of colossal shield volcanoes create variations in atmospheric circulation patterns across the planet.
These changes in circulation can lead to distinct temperature gradients, altering climate dynamics in surrounding areas.
During the Martian summer,
the atmosphere warms significantly, causing the polar ice caps to shrink and releasing carbon dioxide gas.
The immense volcanic structures contribute to heat retention, causing localized warming that further exacerbates these seasonal transformations.
As a result,
specific regions experience pronounced temperature fluctuations, impacting weather patterns and surface conditions.
In contrast, winter brings cold temperatures, leading to the growth of polar ice caps.
The Tharsis Bulge, due to its elevation,
remains comparatively warmer, influencing the timing and extent of ice formation. This differential heating can initiate dust storms, which are prevalent on Mars, creating temporary atmospheric disturbances. The interplay of topography and seasonal change leads to complex interactions between geology and climate. The Tharsis region, with its massive shield volcanoes, acts as both a physical and thermal influence on Martian weather, thereby shaping its seasonal phenomena.
Understanding these relationships provides insights into the planet's evolution and highlights the intricate balance between its geological and atmospheric systems.
Tharsis Bulge, a colossal volcanic province, showcases a unique geological structure that may have profound implications for Mars's climatic history. Its sheer size, encompassing an area greater than that of the entire United States, presents a significant alteration to the planet's topography. This alteration likely influenced atmospheric circulation patterns over millions of years. As volcanic activity released gases, including carbon dioxide and water vapor, it contributed to a warming effect, potentially fostering conditions conducive to ice cap formation. The interplay between volcanic outgassing and climatic shifts remains a critical area of study, as the resulting temperature changes could have facilitated the deposition of ice at the poles. Surface features reveal signs of ancient glacial activity, suggesting that polar ice caps may have formed in response to these shifting conditions. The relationship between the Tharsis Bulge and the polar ice caps provides a fascinating glimpse into Mars's past climate transitions. Evidence indicates that periods of volcanic activity could have alternated with colder epochs, leading to cyclic variations in ice accumulation. Recent observations from orbiters and rovers continue to refine our understanding of these phenomena. The ongoing exploration of the Tharsis region and its volcanic history remains essential for unraveling the complexities of Martian climate evolution and its impact on the planet's polar regions. The Tharsis region, with its immense volcanic structures, plays a pivotal role in shaping Martian weather patterns. The colossal shield volcanoes, including Olympus Mons, exert significant influence on atmospheric circulation. They alter wind patterns and thermal dynamics, affecting weather phenomena across the planet. These elevated landforms create localized climatic conditions, leading to variations in temperature and pressure that can extend for thousands of kilometers. Surface features within this area frequently interact with the thin Martian atmosphere. Dust storms, which can envelop vast swaths of the planet, are often intensified by the thermal gradients established by the Tharsis volcanoes. This phenomenon can disrupt typical weather patterns, causing fluctuations in regional climates. The interplay between the volcanic activity and the atmosphere raises intriguing questions about how these giants might contribute to long-term climatic shifts. Data gathered from orbiters and rovers suggest that the Tharsis region may have once supported a more dynamic atmosphere, possibly rich with water vapor. The remnants of ancient riverbeds and lake deposits hint at a time when weather patterns could have been significantly different. Understanding the correlation between these volcanic structures and Martian meteorological events is essential for reconstructing the planet's climatic history and assessing its potential for sustaining life in the past. The Tharsis region provides crucial insights into Martian plate tectonics theories, a subject of significant interest within planetary science. The immense size of this volcanic plateau, stretching over 2,000 kilometers in diameter, suggests that it has influenced tectonic activity on Mars. Its formation, attributed to a series of colossal eruptions, raises questions regarding the planet's geological history and evolutionary processes. Certain models propose that the Tharsis Bulge could have acted as a kind of anchor point for tectonic movement. Such a structure may have destabilized the lithosphere, leading to the formation of rift valleys and fault lines across the planet's surface. This region's volcanic activity could also have impacted the thermal dynamics of the Martian crust, contributing to variations in tectonic forces over time. Photony of the two volcanoes and the planet's lithosphere reveals a complex interplay of geological forces. Evidence suggests that the bulge's formation may correlate with significant shifts in the planet's rotation and axial tilt. These changes could have influenced climate patterns and atmospheric dynamics, further complicating our understanding of Mars's geological narrative.
Investigating these relationships allows scientists to delineate the mechanisms behind Martian tectonics, shedding light on the processes that shaped not only this region but the entire planet. Understanding Tharsis's role is fundamental to unraveling the history of Mars's surface and its potential habitability. The concept of volcanic superplumes provides valuable insight into the geological forces at play within this region. These immense structures form when magma rises from deep within a planet's mantle, creating vast volcanic activity. Tharsis, with its colossal shield volcanoes, is a prime candidate for the effects of such superplumes. The rise of magma beneath the surface can alter the thermal dynamics of the crust, leading to the formation of large volcanic edifices, such as Olympus Mons, which stands as the tallest volcano in the solar system. The superplume theory posits that these volcanic activities could cause significant changes in a planet's spin and axial tilt over time. As magma accumulates and erupts, the redistribution of mass impacts the planet's overall rotation. In the case of Mars, the formation of Tharsis could have initiated shifts in its axial tilt, subtly influencing climate patterns and the development of surface features. Unhasest than Lofester, this process emphasizes the importance of understanding the interplay between volcanic activity and planetary rotation. Tharsis serves not just as a collection of geological formations, but as a crucial element in the broader narrative of Mars's geological evolution. The implications of such volcanic activity extend beyond mere topographical changes, hinting at a complex history that intertwines geology, climate, and potential habitability. This region, known as the Tharsis Bulge, represents one of the most significant geological features on Mars. It is characterized by a vast volcanic plateau, home to some of the largest volcanoes in the solar system, including Olympus Mons, formed through repeated lava flows and explosive eruptions. This colossal bulge has played a crucial role in shaping the Martian highlands. These highlands, elevated and ancient, encircle the Tharsis region, marking a stark contrast to the lower-lying plains. The formation of the highlands is believed to be linked to the tectonic and volcanic processes initiated by the immense weight of the Tharsis Bulge. As magma rises and accumulates, it alters the planet's crust, leading to the uplift and extensive fracturing observed in surrounding areas. The interplay between volcanic activity and erosion has resulted in a landscape that bears witness to billions of years of Martian history. Erosion, driven by wind and possibly ancient water flows, has sculpted the surface, revealing layers of geological strata. These remnants serve as a record of past environmental conditions, offering insights into the planet's climatic evolution. Understanding the Tharsis Bulge and its influence on Martian geology not only unveils the planet's past but also raises questions about its potential for sustaining life in more favorable epochs. The role of water in shaping Tharsis eruptions is pivotal, influencing volcanic activity and surface morphology. Evidence suggests that liquid water, once prevalent on Mars, interacted with volcanic materials, altering their properties. This interaction led to the formation of explosive eruptions characterized by the release of steam and gas, creating pyroclastic deposits that blanket the surrounding landscape. Observations indicate that when water infiltrates volcanic systems, it can lower the viscosity of magma, facilitating its ascent. These processes result in explosive volcanic events, contributing to the unique geological features found in this region, such as the expansive calderas and fissure systems. The interplay between water and magma is critical for understanding the timing and nature of volcanic activity. The presence of ancient river valleys and lake beds adjacent to volcanic structures further emphasizes this interaction. They suggest that periods of heightened volcanic activity coincided with wetter climatic conditions. These processes may have enhanced the potential for habitability by creating transient environments where liquid water could exist. Continued study of the Tharsis Bulge reveals not only the intricate relationship between water and volcanism, but also the broader implications for planetary evolution. The dynamics of these ancient eruptions contribute significantly to the understanding of Mars' geological history and its capacity to support life. Aront's research techniques employed to study the Tharsis Bulge offer a window into the complex processes that shape planetary bodies. Advanced satellite imaging provides high-resolution data, revealing intricate surface features and volcanic structures. These images allow scientists to analyze the morphology of the region, identifying distinct calderas, fissuras, and lava flows that hint at the evolution of volcanic activity over time. Geophysical surveys enhance this understanding by measuring gravitational and magnetic fields in the vicinity. Variations in these fields suggest the presence of subsurface magma chambers, offering insights into the mechanisms that may still be at play beneath the surface. This information contributes to models that predict how volcanic activity could influence the planet's rotation and axial tilt. Spectroscopy plays a critical role in analyzing surface materials. By examining the light reflected from the Martian surface, researchers can determine the composition of rocks and soils, providing clues about the history of volcanic eruptions and the potential for past volcanic activity to affect the climate. Fieldwork simulations on Earth, replicating Martian conditions, advance knowledge of volcanic processes. These experiments refine techniques for analyzing data returned by future missions, enabling more accurate interpretations of the Tharsis Bulge and its implications for Mars's geological history. Each method contributes to a comprehensive understanding of this remarkable region, revealing the subtleties of a planet shaped by fire and time. Orbital imaging has emerged as a pivotal tool in the geological studies of the Tharsis Bulge, offering an unparalleled perspective on its vast volcanic landscape. High-resolution images captured by satellites provide detailed insights into the structure and composition of these colossal formations. Various wavelengths allow scientists to identify minerals and thermal emissions, helping to reveal the history of volcanic activity and the evolution of the Martian surface. On this, technology has facilitated the mapping of individual volcanoes, uncovering features such as calderas and lava flows that span hundreds of kilometers. By analyzing the size and shape of these geological features, researchers can infer the mechanisms of volcanic eruptions and their frequency. Advanced techniques, including radar and infrared spectroscopy, enhance the ability to detect subtle variations in topography and mineralogy, further deepening the understanding of this region's geological past. Data gathered through orbital imaging also contribute to the assessment of tectonic processes and their relationship to volcanic activity. Observations of deformation patterns reveal insights into the internal dynamics of the planet, indicating how changes in mass distribution can influence its rotational characteristics. These findings underscore the complex interplay between geological forces and planetary evolution, painting a comprehensive picture of Martian history. Each observation adds a layer of knowledge, illuminating the intricate processes that govern this remarkable environment. The Volcanoes of this region has been profoundly enhanced by rover missions, which serve as mobile laboratories on the Martian surface. These robotic emissaries are equipped with a suite of scientific instruments designed to analyze soil composition, atmospheric conditions, and geological formations. By traversing the diverse terrain of the Tharsis Bulge, they gather data that elucidate the history and evolution of these colossal volcanoes. Rovers provide invaluable insights into the volcanic activity that shaped this region. They can assess the chemical makeup of lava flows, revealing the processes that contributed to their formation. This analysis aids in understanding how volcanic eruptions may have influenced the planet's climate and atmospheric dynamics over time. The ability to conduct in situ measurements allows researchers to correlate remote sensing data with ground truth observations, creating a more cohesive picture of Martian geology. The presence of ancient riverbeds and mineral deposits indicates that water once flowed freely, hinting at a more hospitable past. Each mission contributes to a growing repository of knowledge, facilitating a deeper comprehension of planetary processes. Insights gained from these rovers extend beyond Tharsis, informing theories about volcanic activity and planetary evolution across the solar system. The Mars Reconnaissance Orbiter has played a pivotal role in advancing the understanding of the Tharsis region. Equipped with high-resolution imaging capabilities, it captures detailed surface features, revealing the intricate geology of the vast volcanic structures. This satellite continually monitors key areas, allowing scientists to observe changes over time, which is instrumental in assessing the dynamic nature of these colossal volcanoes. Data collected from the orbiter contributes to mapping the extent of lava flows, calderas, and various other geological formations. These observations help clarify the processes that shaped the Tharsis Bulge and elucidate the potential interactions between volcanic activity and the planet's atmosphere. By examining the mineral composition of surface materials, the orbiter aids in identifying the history of water and ice in the region, enhancing the understanding of Mars' climatic evolution. The ability to analyze the morphology of the volcanoes offers insights into their eruptive history and frequency. This information is crucial for constructing models that predict future volcanic behavior, which may influence both the planet's geology and its potential habitability. The continuous flow of data from the Mars Reconnaissance Orbiter facilitates a comprehensive analysis of the Tharsis region, contributing to a broader understanding of planetary processes and their implications across the solar system. The Tharsis region, with its colossal shield volcanoes, has a profound impact on the Martian hydrosphere. This area, characterized by immense geological formations, appears to influence the distribution of water ice beneath the surface. Volcanic activity historically released gases into the atmosphere, which may have contributed to a warmer climate, allowing liquid water to exist. The interaction between volcanic processes and hydrological features is evident in the various channels and valleys that crisscross the landscape. Observations indicate that the presence of water ice is closely linked to the volcano's thermal dynamics. The geothermal heat generated by these giants melts surrounding ice, creating a network of subsurface reservoirs. These reservoirs likely played a role in shaping ancient river systems, as well as the current distribution of polar ice caps. The potential for liquid water, even in a dormant state beneath the surface, raises questions about past climates and the possibility of life. Analysis of surface features, such as the distinctive outflow channels, reveals a history of water movement that aligns with volcanic activity. The interplay between the Tharsis Bulge and the Martian hydrosphere underscores the complexity of planetary evolution. Understanding this relationship offers insight into the processes that govern not just Mars, but also other celestial bodies where similar dynamics may exist. Kohöristim vösörishan bys Alsatian Azorican Tukaladio. Once-mel dynamics may exist. The potential for future eruptive activity in this region remains a topic of considerable interest among scientists. The Tharsis Bulge, characterized by its vast shield volcanoes, holds evidence suggesting that it may not be entirely dormant. Geological assessments indicate that some formations exhibit signs of relatively recent activity, hinting at a dynamic past. These characteristics include lava flows that have not undergone significant erosion, implying a timeline that could extend into the millions of years. The presence of volcanic gases trapped within the surface materials further supports the notion that these giants may yet awaken. Such gases could be indicative of underlying magma movement, a process that precedes volcanic eruptions. This subtle interplay between tectonic and magmatic forces is a pivotal focus of ongoing research. In monitoring the Tharsis region, scientists utilize high-resolution imaging and spectral analysis to detect any shifts in surface morphology or thermal anomalies, which could signal imminent activity. The implications of a resurgence in volcanic activity extend beyond Mars itself. Understanding the behavior of these colossal structures may illuminate the volcanic processes on other rocky planets and moons throughout the solar system. Ongoing missions to gather further data could eventually reshape our comprehension of planetary evolution and the long-term stability of planetary climates. Insights gained here will resonate through the scientific community, fostering a deeper understanding of planetary dynamics. Geothermal gradients on Mars exhibit a distinct pattern influenced significantly by the Tharsis Bulge. This region, characterized by its colossal shield volcanoes, generates localized thermal anomalies that impact the thermal structure of the surrounding crust. The immense mass of these volcanoes contributes to an elevated geothermal gradient, creating a stark contrast with the less active regions of the planet. 1 to Vihuo, heat flow from the interior rises towards the surface, resulting in variations in temperature that can reach up to several hundred degrees Celsius. Such a gradient affects not only mineral formation but also the potential for subsurface water reservoirs. These thermal dynamics shape the geological history of Mars, influencing erosion patterns and the stability of the soil. The presence of volcanic activity acts as a thermal engine, driving processes that may have implications for the planet's habitability. Fluctuations in heat can lead to the melting of subsurface ice, facilitating the transport of materials and possibly creating transient liquid water environments. Vibe regions adjacent to Tharsis display signs of ancient hydrothermal systems, indicating the potential for diverse chemical interactions. These findings open avenues for understanding the planet's past, suggesting that Tharsis plays a crucial role in the evolution of its geological and possibly biological landscape. The interplay of heat and geology reveals the complexity of Martian processes. Geophysical surveys of this region utilize a variety of techniques to unravel the intricacies of its volcanic features. Radar imaging, for example, penetrates the surface, revealing the subsurface structures and architecture of the enormous shield volcanoes. These techniques allow scientists to visualize the layering of lava flows and assess the geological history that has shaped this expansive area. Gravity measurements provide additional insights into the subsurface density variations, indicating the presence of magma chambers or more solidified rock formations beneath the surface. This data suggests that the Tharsis Bulge is not a uniform structure but rather a complex arrangement of materials shaped by dynamic volcanic activity over millions of years. Magnetometry also plays a key role in these investigations. By measuring the magnetic fields, researchers can infer the composition of the crust, revealing how different volcanic materials have impacted the planet's magnetic history. Thermal imaging complements these methods, assessing the heat emitted by the volcanoes and pinpointing areas of recent activity or cooling. Findings indicate that some of these volcanoes might still be geologically active, possibly even influencing the planet's rotation. Each survey contributes to a comprehensive understanding of how these massive features interact with the Martian environment, enhancing our knowledge of planetary evolution. The effects of the Tharsis Bulge extend deeply into the Martian crust, influencing deformation patterns across vast regions. This region, dominated by colossal shield volcanoes, exerts a gravitational pull that alters the distribution of mass within the crust as the magma beneath the surface moves and shifts. It creates a complex interplay of stresses in the surrounding rock. This process induces significant changes in the crustal structure, resulting in both uplift and subsidence. Surface observations reveal a network of faults and fissuras extending outward from the volcanic centers. These features indicate that the crust has responded to the immense weight of the Tharsis Massif by bending and cracking. In some areas, the crust has thickened due to the accumulation of volcanic material, while in others, it has thinned, revealing a stratigraphy that tells the story of millions of years of geological activity. The influence of Tharsis is not limited to localized changes. The redistribution of mass can lead to broader tectonic adjustments across the planet. Measurements of seismic activity correlate with volcanic eruptions, suggesting that the dynamic processes within Tharsis play a role in Martian seismicity. Understanding these interactions provides insights into the planet's geological history and the mechanisms driving its evolution over time. Each observation enriches the narrative of Mars, revealing a world shaped by its own geological forces. The Tharsis region stands as a monumental feature on Mars, characterized by its vast volcanic plateaus and towering volcanoes. These formations, including the colossal Olympus Mons, exert considerable influence on the planet's geology. Over time, the enormous mass of this volcanic province may have contributed to changes in Martian seismicity. The weight of Tharsis compresses the crust beneath, potentially causing fractures and alterations in the tectonic landscape. Seismological data indicate that the presence of these immense geological structures correlates with increased seismic activity. The volcanic systems may serve as a catalyst for tectonic shifts, creating a delicate balance of forces that shape the Martian surface. As the crust responds to the stress from the Tharsis Bulge, it creates a complex network of faults and fractures, leading to a dynamic environment. Volcanic outgassing and the potential release of subsurface water may further affect the planet's seismic behavior. While the Tharsis region has been relatively dormant in recent geological terms, the possibility of future volcanic events lingers with influencing not only local geology, but also contributing to broader changes in Martian atmospheric conditions. The intricate interplay of forces within this region continues to captivate scientists, revealing insights into the planet's past and its ongoing evolution. Each study of Tharsis contributes to a deeper understanding of Martian geology. Magma dynamics within this region reveal a complex interplay of geological processes. The Tharsis Bulge, home to the largest volcanoes in the solar system, serves as a significant site for studying the movement and evolution of magma beneath the Martian surface. These colossal formations indicate a history of intense volcanic activity, suggesting that vast quantities of molten rock have risen from the mantle to the crust over millions of years. This ascent of magma results from varying pressures and temperatures, leading to the formation of large volcanic edifices. The presence of lava channels and extensive plains around these volcanoes indicates that once, magma flowed freely, reshaping the landscape and influencing the planet's atmospheric conditions. The interplay between solid crust and molten rock contributes to the understanding of heat transfer and the thermal evolution of Mars. Variations in magma composition further illuminate the geological history, revealing insights into the differentiation processes that have occurred within the planet's interior. The large volume of volcanic material ejected has potential implications for the Martian atmosphere, impacting its ability to retain heat and serve, in turn, influencing climate patterns throughout its history. Studying these dynamics offers critical insights into how volcanic regions can influence planetary evolution on a broader scale, providing a window into the past and future of Mars. Historical interpretations of the Tharsis Bulge reveal a landscape that has captured human imagination for centuries. Early astronomers, armed with rudimentary telescopes, gazed at the red planet and speculated on its surface features. They observed the vastness of this region, noting its unusual characteristics, which sparked theories about its formation and purpose. The prominent volcanoes, such as Olympus Mons, were perceived as signs of a vibrant, possibly habitable world. Astronomers of the late 19th century, including notable figures like Giovanni Schiaparelli and Percival Lowell, contributed to a growing narrative of Martian civilization. They described intricate canals and patterns, attributing them to advanced beings that might inhabit the planet. This perspective, while later debunked, underscored the significance of the Tharsis Bulge as a focal point in the quest to understand Mars. The prominent volcanic structures were interpreted not merely as geological formations, but as potential indicators of life-sustaining processes. Such notions persisted into the mid-20th century, when space exploration began to transform our understanding. Photographs captured by orbiters revealed the true nature of the Tharsis region, unveiling a stark, desolate beauty marked by ancient lava flows and immense calderas. Each image added another layer, reshaping the narrative surrounding this intriguing feature of Mars. Various theories attempt to elucidate the formation of the Tharsis Bulge. One prominent hypothesis suggests a massive volcanic hotspot beneath the Martian crust. This region may have experienced intense geothermal activity, leading to the uplift of surface material over millions of years. Successive eruptions could have deposited vast quantities of lava, gradually building up the enormous shield volcanoes that define this area today. Another theory considers the impact of tectonic processes. The strain from tectonic plate movements could have contributed to the bulge's formation. As magma accumulated beneath the crust, it might have found its way to the surface through fissures, resulting in both volcanic activity and the warping of the crust itself. This geological interplay could explain the immense size and elevation of the Tharsis region compared to the surrounding plains. Some researchers propose a combination of these mechanisms, suggesting that the Tharsis Bulge is the result of both volcanic activity and tectonic forces working in concert. Each eruption may have contributed to the structural integrity of the bulge, reinforcing it against gravitational stresses. Understanding the dynamics of this region not only sheds light on Mars's geological history, but also provides insight into planetary formation processes. The Tharsis Bulge stands as a testament to the complexities inherent in planetary evolution, revealing much about the red planet's past. Comparative planetology unveils striking contrasts between the Tharsis Bulge and Earth's major volcanic regions. This vast Martian feature, characterized by its colossal shield volcanoes, dwarfs Earth's largest counterparts, Olympus Mons. The most prominent of these volcanoes rises approximately 22 kilometers above the surrounding plains, significantly exceeding the elevation of Mount Everest, Earth's apex. Such dimensions render it a dominant force in shaping Martian geology. In contrast, Earth hosts a diverse array of volcanic formations, from the active stratovolcanoes of the Pacific Ring of Fire to the shield volcanoes of Hawaii. These terrestrial formations result from dynamic plate tectonics, a process absent on Mars. The stationary nature of the Martian crust has led to the formation of enormous, singular volcanic edifices, as opposed to Earth's more fragmented volcanic landscape. Eruptive histories also differ markedly. While Earth's volcanoes exhibit a variety of eruptive styles influenced by tectonic interactions, Tharsis's volcanoes reveal prolonged periods of inactivity, punctuated by massive eruptions. This cyclical activity suggests a different thermal regime and magma generation process on Mars, potentially linked to its unique mantle dynamics. Understanding these differences deepens insights into planetary formation and evolution, illuminating the path taken by Mars as it diverged from Earth's more geologically active trajectory. Volcanism plays a pivotal role in shaping planetary atmospheres, influencing chemical compositions and climatic conditions on Mars. The Tharsis Bulge, home to some of the largest volcanoes in the solar system, provides a compelling case study. These immense structures, such as Olympus Mons and Ascraeus Mons, stand as silent sentinels over a once dynamic landscape, their vast calderas hinting at a prolonged history of eruptive activity. Eruptions release gases like carbon dioxide, water vapor, and sulfur dioxide into the atmosphere. This process contributes to the greenhouse effect, which can warm a planet's surface and sustain liquid water. For Mars, the substantial volcanic activity during its formative years likely helped cultivate a more robust atmosphere. Over time, however, a significant decline in volcanism resulted in diminished atmospheric pressure and temperature, leading to the arid conditions observed today. The interplay between volcanic activity and atmospheric evolution also impacts surface geology. Ejecta from volcanic events can alter terrain, creating new landscapes and sediments that further interact with atmospheric elements. Despite the current dormancy of Martian volcanoes, their past activity continues to shape the planet's atmospheric history, offering insights into climate evolution and potential habitability. Understanding these processes not only enhances knowledge of Mars, but also provides broader implications for other planetary bodies across the cosmos. The Tharsis Bulge serves as a significant contributor to Mars's thermal history. This extensive volcanic region, characterized by its prominent shield volcanoes, has influenced the planet's geological evolution over millions of years. The formation of the bulge is believed to have altered the distribution of thermal energy within the Martian crust through a process called volcanotectonics. The immense weight of the bulge has created stresses that could lead to the fracturing of the crust, facilitating the release of heat. Thermal modeling suggests that these volcanic activities may have played a crucial role in maintaining subsurface temperatures, potentially allowing for the existence of liquid water in the past. With eruptions occurring over a protracted period, the heat generated would have contributed to a more dynamic thermal environment. Volcanic gases released during these eruptions could have also influenced the atmosphere, thickening it and creating conditions more favorable for sustaining liquid water. The relationship between the Tharsis Bulge and Mars's thermal history highlights the interplay between geological processes and atmospheric changes. Evidence of ancient river valleys and lake beds provides a stark contrast to the current arid landscape, suggesting that volcanic activity and thermal dynamics once shaped a much different planet. This region remains a focus for understanding the complex history of Mars and its potential for habitability. Modeling the impact of volcanism on planetary spin reveals profound insights into the evolution of celestial bodies. The Tharsis Bulge Planetaries, with its colossal shield volcanoes, provides a unique scenario for examining how volcanic activity influences rotational dynamics. These massive structures, towering over the Martian landscape, exert gravitational forces that can alter the planet's moment of inertia as magma accumulates beneath the crust. Its redistribution can lead to shifts in the balance of mass. When eruptions occur, the ejected material contributes to changes in the distribution of mass on the surface. Over geological timescales, this can result in measurable variations in the planet's spin rate and axial tilt. Simulations of this process suggest that significant volcanic events could cause oscillations in spin, potentially leading to changes in climate and atmospheric conditions. The Tharsis region's volcanic activity may have played a role in shaping Mars's axial tilt, influencing the planet's climate cycles. These cycles could affect the stability of liquid water on the surface, a critical factor for potential habitability. Understanding these dynamics not only enhances knowledge of Mars, but also offers a framework for examining similar processes on other planetary bodies. The implications of such volcanic activity extend beyond Mars, contributing to the broader understanding of planetary evolution in the solar system. The theoretical analysis suggests that the Tharsis Bulge, with its vast volcanic structures, may have played a significant role in altering Mars's rotational dynamics. This region, characterized by its colossal shield volcanoes, creates an uneven distribution of mass across the planet's surface. Such mass concentrations can induce a phenomenon known as axial precession, where the orientation of a planet's rotation axis gradually shifts over time. The redistribution of mass within this geological formation may lead to changes in rotational speed. Modeling indicates that the immense weight of the Tharsis volcanoes could influence the planet's moment of inertia, effectively causing variations in its rotational period. These volcanic edifices, towering above the Martian surface, contribute to a delicate balance between gravitational forces and centrifugal effects. In addition to altering rotation rates, the Tharsis region may impact the stability of Mars's axial tilt. Fluctuations in this tilt can have profound implications for climate patterns, potentially affecting the distribution of ice and liquid water in the planet's past. Such changes in climate could have influenced the development of Martian surface features and contributed to the planet's overall geological history. Understanding these dynamics offers insights into how large-scale geological processes can affect planetary behavior, shaping the evolution of Mars and similar celestial bodies throughout the cosmos. The impact of massive volcanic eruptions on planetary dynamics is profound and multifaceted. These geological events can alter a planet's mass distribution, leading to shifts in its rotational axis and overall spin on Mars. The colossal shield volcanoes of the Tharsis region demonstrate this phenomenon vividly. They stand as monumental structures, their immense heights and volumes capable of redistributing mass across the Martian surface. When such volcanoes erupt, they expel vast quantities of material into the atmosphere, potentially affecting the planet's climate. The released gases and ash can create a temporary haze, altering solar radiation absorption and influencing temperature patterns. This interaction between volcanic activity and atmospheric conditions may lead to feedback loops that further modify planetary behavior. In addition to climate implications, the redistribution of mass can induce tectonic responses. The shifting of enormous volcanic edifices might trigger seismic activity, reshaping the crust in ways that reflect ongoing geological processes. Over time, these eruptions contribute to the long-term evolution of planetary surfaces, influencing erosion patterns and sediment deposition. Scientific studies continue to analyze the relationship between volcanic activity and planetary dynamics. Insights gleaned from Mars can inform our understanding of similar processes on Earth and other celestial bodies, revealing a universal connection that transcends individual worlds. The Tharsis volcanic region plays a pivotal role in shaping the historical climate oscillations of Mars. This immense uplift, characterized by its vast shield volcanoes, exerts a gravitational influence that affects the planet's axial tilt and orbital dynamics. Variations in these parameters have profound implications for climate patterns over geological timescales. As volcanic activity within Tharsis fluctuated, the release of gases, such as carbon dioxide and water vapor, contributed to atmospheric changes. These gases can alter the greenhouse effect, leading to potential warming or cooling of the Martian surface. During periods of heightened volcanic activity, the climate may have shifted towards warmer, wetter conditions, fostering the possibility for liquid water to exist on the surface. Conversely, times of dormancy could have initiated colder, drier phases, limiting the availability of liquid water and further shaping the planet's geophysical landscape. The interplay between the Tharsis region and climate demonstrates a complex relationship. These fluctuations are recorded in sedimentary deposits, which reveal oscillations between wet and dry epochs. Analyzing these layers allows scientists to reconstruct Mars's climatic history, providing a clearer understanding of how volcanic activity influences planetary environments. Investigations continue to unveil the intricate connections between Tharsis, climate, and the potential for past habitability, enriching our knowledge of planetary evolution across the solar system. The potential for human exploration of Tharsis presents a fascinating array of opportunities and challenges. This region, dominated by colossal volcanoes, offers insights into geological processes and the history of Mars itself. The presence of ancient lava flows and vast calderas indicates a dynamic past where volcanic activity played a critical role in shaping the Martian landscape. Human missions may focus on these towering formations, with scientists seeking to understand their composition and the implications of past eruptions. The unique geology could serve as a resource for in situ utilization, providing materials for construction or fuel. Investigations into the potential for subsurface water ice could further enhance the viability of sustained human presence. Safety remains a primary concern, given the unpredictable nature of volcanic activity. Understanding the tectonic stability of this region is essential, as any exploration must account for the risks associated with dormant or active volcanism. Advanced robotics and remote sensing technologies may play a key role in initial surveys, allowing for the collection of data without direct human intervention. Plans for future missions could also integrate the study of Tharsis into broader Martian exploration strategy. Each new discovery here may illuminate not only the history of Mars, but also the broader mechanisms of planetary evolution influencing the trajectory of human endeavors beyond Earth. The Tharsis Bulge serves as a compelling case study in understanding volcanic structures and their influence on a planet's geophysical characteristics. This immense region, characterized by its towering volcanoes and expansive plains, provides insight into the internal processes that shape planetary bodies. The massive shield volcanoes within the bulge, including Olympus Mons, reveal the extent of volcanic activity and the potential for heat retention within a planet's crust. Investigating these formations can deepen comprehension of volcanic activity elsewhere in the solar system and beyond. The dynamics observed in the Tharsis region may parallel those found in exoplanets that exhibit similar geological features. Observations suggest that the presence of significant volcanic activity can affect atmospheric composition and climate stability, factors essential for habitability. This relationship between volcanism and planetary evolution holds implications for the formation of atmospheres, the development of liquid water, and the establishment of conditions conducive to life. By analyzing volcanic systems like Tharsis, scientists can refine models predicting the habitability of distant worlds. Understanding the mechanisms behind such geological phenomena on Mars may enable more accurate assessments of exoplanetary environments, potentially guiding future exploration missions. The interplay between volcanism and planetary development thus remains a crucial focal point in the quest to unravel the mysteries of the universe. Tharsis, an expansive volcanic plateau on Mars, serves as a pivotal reference point in understanding the planet's geological history. Dating the surface surrounding this region provides insights into the evolution of volcanic activity. This area exhibits remarkable features, including the largest volcanoes in the solar system, which display varying degrees of erosion and impact cratering. Analysis indicates that the age of these surface materials varies significantly, revealing a timeline of volcanic events interspersed with periods of relative dormancy. Crater counting techniques have been employed to establish the ages of different terrains. Regions with fewer craters are deemed younger, suggesting active volcanism, while heavily cratered areas indicate ancient surfaces that have withstood the test of time. The relationship between Tharsis and surface age dating highlights the volcanic influence on Martian climate and atmosphere. When major eruptions occurred, they contributed to atmospheric changes that could have affected surface conditions. The resulting ash deposits and lava flows add layers to the geological record, complicating the dating process. Our investigations into the potential for past habitability are intertwined with this geological chronology. Understanding the timeline of Tharsis offers a window into the environmental conditions that may have existed, impacting the possibility of life on Mars and shaping its evolution over billions of years. The structural integrity of the Tharsis volcanoes reveals insights into their formation and longevity. Extensive stress analysis indicates that these colossal edifices are not merely geological features, but also complex systems shaped by internal and external forces. Each volcano, towering high above the Martian surface, experiences immense gravitational stresses due to their sheer mass. The interaction of tectonic activity and volcanic processes creates a dynamic equilibrium that influences their stability. Surface cracking and subsidence patterns observed across this region provide evidence of ongoing geological adjustments. These cracks serve as indicators of stress distribution, revealing how forces propagate through the volcanic structures. Fine-grained data from topographic maps and satellite imagery allow scientists to model potential failure points, suggesting that certain areas may be more susceptible to collapse over time. The history of Tharsis volcanoes reflects not only the planet's geological past, but also its thermal evolution. Heat from beneath the crust has played a significant role in shaping the landscape, contributing to the growth and maintenance of these towering giants. Measurements of the surrounding plains reveal the extent of lava flows, which have spread across vast distances, further complicating the stress landscape. The ongoing analysis of Tharsis enhances the understanding of Martian geology. offering clues about how similar volcanic systems might evolve elsewhere in the solar system. Assessing the risk of future eruptions in this region involves examining geological history and current activity patterns. Evidence indicates that the Tharsis volcanic system has experienced extensive eruptions over millions of years, leaving behind a landscape characterized by vast shield volcanoes and expansive lava plains. The age and distribution of these volcanic features suggest a complex timeline of activity, with some structures potentially still harboring the capacity for eruptions. Geologists utilize various methods to monitor the area, including the analysis of surface deformation, heat flow, and gas emissions. Subtle shifts in the ground can indicate magmatic movement beneath the surface, while thermal anomalies may reveal areas of heightened volcanic activity. Understanding the composition of underlying materials provides insight into the likelihood of future eruptions. Additionally, the potential impact of eruptions extends beyond local phenomena. Eruptions could influence atmospheric composition, creating dust clouds that may affect Martian weather patterns and solar radiation absorption. The consequences of such events necessitate a comprehensive understanding of eruption dynamics and risk assessment models. Current models suggest that while the likelihood of an imminent eruption remains low, the historical activity implies a future risk, emphasizing the need for continuous monitoring. This vigilance is crucial for unraveling the enigmatic processes that govern Tharsis and similar volcanic environments throughout the solar system. Cultural reflections of this region have profoundly shaped humanity's understanding of Mars. The Tharsis Bulge, with its colossal volcanoes and expansive plains, serves as a canvas for various interpretations, inspiring literature, art, and scientific inquiry. These towering formations, including Olympus Mons, evoke images of alien landscapes, stirring curiosity and wonder about the potential for life beyond Earth. Literary works often depict Mars as both a distant world of adventure and a cautionary tale of hubris. In fiction, the Tharsis region emerges as a battleground for human exploration and confrontation with the unknown. It symbolizes the allure of the extraterrestrial, manifesting in narratives that ponder human existence and the quest for knowledge. Artistic portrayals capture the Martian surface's stark beauty, reflecting its haunting desolation and the grandeur of its geological features. The interplay of light and shadow across the Tharsis Bulge creates an otherworldly atmosphere, inspiring visual artists to interpret its essence through various mediums. Scientific endeavors have also been driven by the desire to understand this region. The quest for knowledge about Tharsis not only enhances our comprehension of planetary processes, but also signifies humanity's intrinsic need to explore and connect with the cosmos. The cultural significance of this volcanic expanse extends beyond its physical characteristics, embedding itself into the collective consciousness of humankind. Tharsis serves as a pivotal focus in astrobiological studies, presenting unique conditions for examining the potential for life beyond Earth. This region, dominated by massive shield volcanoes and also the Tharsis itself, features a complex interplay of geological processes that may have influenced past environments. The sheer scale of the Tharsis volcanoes suggests an extended period of volcanic activity, contributing to atmospheric chemistry and possibly providing essential elements for life. Investigating these landforms uncovers vital information about ancient Martian climates, the evidence of past lava flows, and the presence of minerals such as clays indicate that liquid water may have existed on the surface. This finding remains crucial, as water is a fundamental prerequisite for life as it is known. In addition to geological formations, the potential for subsurface habitats is of significant interest. The interactions between volcanic activity and subsurface water may have created niches where microbial life could thrive. Surviving under the harsh Martian surface, the exploration of this region has been intensified by rover missions, which have collected data on mineralogy and atmospheric composition. Insights gained from these studies enhance the understanding of habitability in extreme environments, guiding future missions to seek signs of ancient life and assess the planet's potential for supporting life in the future. The Tharsis region, characterized by its immense volcanic structures, influences Martian meteorology in profound ways. The 4 primary volcanoes dominate the landscape, towering over the surrounding plains and casting long shadows across the surface. Their enormous size alters local atmospheric dynamics, creating variations in temperature and pressure. These giants, with their calderas and lava flows, can significantly affect wind patterns. The heat emitted from volcanic activity warms the nearby atmosphere, leading to localized updrafts. This interaction between the terrain and the atmosphere fosters the development of unique weather systems. Dust storms, common across Mars, can be intensified by the thermal anomalies created by these volcanic formations as they disrupt typical airflow and generate turbulence. Precipitation on Mars remains scarce, yet studies suggest that Tharsis may play a role in the formation of clouds and potential frost. The cooling effect of the higher altitudes impacts humidity levels, making the region a point of interest for understanding the planet's climate variability. Observations indicate that these volcanic edifices may also contribute to the seasonal changes in surface albedo, affecting the absorption and reflection of sunlight. These interconnected systems highlight the intricate relationship between volcanic activity and atmospheric conditions, drawing attention to the importance of Tharsis in the broader context of Martian climate and habitability research. Analyzing the gravitational field of the Tharsis Bulge reveals crucial insights into the planet's geological and atmospheric dynamics. This region, characterized by its colossal shield volcanoes, exhibits a gravitational anomaly that suggests significant mass concentrations beneath the surface. These variations in gravitational pull provide valuable data about the subsurface structure and composition of the Martian crust. The gravitational field is influenced by the density and distribution of volcanic materials, which can vary dramatically across the landscape. Such disparities indicate not just the presence of volcanic formations, but also the potential for ancient magma reservoirs and tectonic activity. As researchers study these gravitational patterns, they can infer the processes that shaped this remarkable region over millions of years. The implications extend beyond geology. Understanding the gravitational influences can shed light on the planet's rotational dynamics. The mass distribution may affect Mars's tilt and spin, which, in turn, impact seasonal and climatic patterns. Tharsis Bulge serves as a natural laboratory for studying these relationships, offering clues about the planet's past and potential for future habitability. The ongoing analysis of gravitational anomalies continues to refine models of Martian evolution, further enhancing our understanding of this complex and dynamic system. Insights derived from these studies contribute to a more comprehensive picture of Mars' climatic history and its evolving landscape. The Tharsis region serves as a crucial window into Mars's magmatic history, revealing a landscape shaped by immense volcanic activity. Towering over this expanse, the colossal volcanoes stand as silent witnesses to a time when the planet was geologically active. The presence of these formations indicates that the Martian crust underwent significant transformations driven by internal forces. Evidence suggests that the formation of the Tharsis Bulge was not a singular event, but rather a series of eruptions that occurred over millions of years. This continuous volcanic activity contributed to the thickening of the crust and the alteration of the planet's rotational dynamics. The sheer volume of material ejected during these eruptions played a role in redistributing mass across the surface, which in turn affected the planet's axial tilt and spin. Geological features within this region, such as fissuras and lava flows, provide insights into the composition of the Martian crust. Analysis of the volcanic materials reveals a diverse array of minerals, indicating complex magmatic processes. In addition, the relative ages of these structures, determined through crater counting, allow scientists to piece together a timeline of volcanic activity, creating a narrative of Mars's geological evolution. Each layer tells a story, contributing to the understanding of a world that once harbored conditions far different from those observed today. The influence of this massive volcanic region extends beyond its immediate surroundings, affecting surface erosion processes across the entire planet. The colossal shield volcanoes, towering high above the Martian landscape, significantly alter local gravitational forces, which in turn impact sediment transport and atmospheric dynamics. Erosion is not merely a matter of wind and water, it is sculpted by geological giants that dominate the horizon. The presence of Tharsis generates localized weather patterns, leading to variations in wind strength and direction. These changes facilitate the redistribution of dust and fine particles, creating a more dynamic surface environment. Channels carved into the crust exhibit the marks of both sudden and gradual erosion, revealing complex interactions between volcanic activity and atmospheric phenomena. They serve as pathways for potential liquid flow, highlighting the historical interplay between geology and climate. In the absence of a protective magnetic field, the surface is bombarded by cosmic radiation. This exposure accelerates weathering processes, breaking down rocks into smaller fragments. The resulting regolith, rich in minerals, forms the basis for future geological evolution. Through these mechanisms, Tharsis not only shapes the present landscape, but also influences long-term planetary development, illustrating the intricate balance between volcanic activity and erosive processes on Mars. Each feature, a testament to a history woven into the fabric of this arid world. The Tharsis Bulge serves as a natural laboratory for understanding the complex processes of volcanisms. This expansive region, dominated by an array of massive shield volcanoes, Abenes tenate volcanoes, Aviquatis toptiformes, provides vital insights into the geological evolution of Mars. It reveals how volcanic activity has shaped not only the surface but also the very dynamics of the planet's rotation. The size and distribution of these colossal structures suggest a prolonged period of volcanic activity, one that significantly altered the planet's crust. Each edifice, such as Olympus Mons, stands as a monument to the power of molten rock, showcasing the ability of volcanic eruptions to create and reshape landscapes over eons. The age of these formations indicates a potential link to the planet's thermal history, offering clues about its cooling processes and internal structure. Geological surveys reveal that the Tharsis region is characterized by unique lava flows and extensive fracture systems. These features hint at a complex interplay between tectonic and volcanic forces. Understanding these interactions can illuminate broader questions about planetary formation and the potential for life in similar environments. The implications extend beyond Mars, as comparisons with Earth and Venus may reveal universal patterns of volcanic behavior. This region invites ongoing exploration, promising to enhance the comprehension of planetary dynamics within our solar system and beyond. Historical cartographic studies of this region reveal a gradual evolution in understanding and representation. Early observations from Earth, initially based on telescopic imagery, depicted a landscape shrouded in mystery. The limited technology of the time rendered vague outlines of the Tharsis Bulge, with artists and astronomers attempting to capture the essence of its vastness. With advancements in imaging techniques, the arrival of spacecraft provided unprecedented detail. The Viking missions in the 1970s unveiled a more intricate topography, revealing the grandeur of the towering volcanoes and expansive plains. These findings prompted a shift in cartographic representation, emphasizing accurate scales and topological features. Subsequent missions, including Mars Global Surveyor and Mars Reconnaissance Orbiter, further refined these maps. Enhanced resolution allowed for the identification of geological formations and the intricate interplay between ancient lava flows and impact craters. This meticulous work transformed the understanding of volcanic activity and its implications for the planet's evolution. Tharsis map represents not just a collection of features but a narrative of exploration itself. The pursuit of understanding has led to a more nuanced depiction of this colossal region. These evolving maps serve as essential tools for scientists, aiding in the assessment of volcanic features and their potential influence on planetary rotation and climate. The search for past life on Mars often gravitates toward Tharsis, a vast volcanic plateau that holds secrets of the planet's geological evolution. This region, characterized by its towering shield volcanoes and expansive plains, presents a compelling case for ancient habitability. The presence of water, once abundant in liquid form, is a critical factor in assessing the potential for life. Volcanic activity could have created environments where microbial life might have thrived, particularly in the subsurface layers that may have remained protected from harsh surface conditions. Studies suggest that eruptions in this region could have released gases and nutrients, fostering suitable habitats. The interplay between volcanic activity and water is essential, as it affects both the climate and the chemical composition of the Martian surface. Layers of sediment and volcanic rock serve as archives, preserving evidence of past environments. Explorations by rovers and orbiters continue to analyze these geological formations, searching for biosignatures or organic compounds that may indicate previous life forms. Tharsis acts as a focal point in these investigations, with its unique geology providing clues about the planet's climatic history. Understanding the dynamics of volcanic processes here enhances comprehension of the broader Martian system and its capacity to support life in epochs long past. The potential for resource extraction in this region presents intriguing possibilities. Rich deposits of essential minerals and elements lie beneath the surface, shaped by the extensive volcanic activity that has defined the landscape. This area is known to contain significant quantities of water ice, a vital resource for future exploration and habitation. Water, when extracted, can be utilized for consumption, agriculture, and as a component in the production of rocket fuel. Geological studies suggest that the Tharsis Bulge is also rich in various metals, such as iron, nickel, and cobalt. These resources could support the construction of infrastructure necessary for sustained human presence. The composition of the soil, influenced by the eruption of ancient volcanoes, may also yield critical materials for technological advancements. Mining operations in this environment would face unique challenges, including the thin atmosphere and harsh conditions. Nevertheless, advancements in robotics and remote operations could mitigate many risks. The extraction of resources from the Tharsis region could not only support human activities on Mars, but also create economic incentives for further exploration. In addition, understanding the resource distribution may illuminate past volcanic activity, revealing insights into the planet's geological history. This intricate relationship between volcanic processes and resource availability underscores the Tharsis Bulge's significance in the quest for sustainable life beyond Earth. The gravitational pull exerted by the Tharsis Bulge alters the planet's axial tilt and orbital eccentricity. This region, dominated by massive shield volcanoes, acts as a significant contributor to the complex dynamics of Mars' rotation. Changes in mass distribution due to volcanic activity shift the balance of the planet, leading to minor variations in its axial tilt over geological timescales. These fluctuations affect climate patterns, influencing the potential for liquid water stability on the surface. The volcanoes, towering above the surrounding plains, contain vast amounts of ice and carbon dioxide, essential for understanding past climate conditions. The Tharsis Bulge's influence extends beyond mere topography. It plays a crucial role in the long-term climatic evolution of Mars. The eccentricity of Mars's orbit, which oscillates between nearly circular and more elliptical configurations, is significantly impacted by the gravitational interactions with the Tharsis Bulge. Such changes can lead to substantial shifts in solar radiation received by the planet, further altering temperature regimes and atmospheric pressure. Over millions of years, these variations could facilitate or hinder the development of stable environments suitable for life. The interplay between volcanic activity and orbital mechanics thus remains a pivotal factor in the historical and future habitability of Mars, offering insights into planetary evolution across the solar system. The dynamics of the Tharsis Bulge extend beyond volcanic activity, influencing atmospheric phenomena such as dust storms. This region, dominated by several massive shield volcanoes, generates localized heating effects that can alter wind patterns. These alterations contribute to the initiation and sustenance of Martian dust storms, also Marsis turles abatingjiton, which can envelop vast portions of the planet for weeks at a time. Dust storms occur when fine particles are lifted from the surface, propelled by the combination of solar heating and atmospheric turbulence. The sheer scale of these storms can reach hundreds of kilometers in diameter, sometimes merging into global events. During these occurrences, visibility diminishes significantly, and temperatures can fluctuate dramatically, affecting both the surface and upper atmosphere. The interaction between the Tharsis Bulge and dust storms creates a feedback loop. The elevated terrain influences the distribution of heat, impacting the atmospheric pressure and, consequently, the intensity of wind current. This interplay may lead to enhanced storm development, which in turn can redistribute sediments across the Martian surface. The sustained dust coverage alters albedo, affecting how solar radiation is absorbed or reflected. Such changes can influence climatic conditions over extended periods, offering a glimpse into the intricate relationship between geology and climate on Mars. Understanding these processes provides essential knowledge about the planet's past and potential for future habitability. Future missions targeting this region aim to enhance understanding of the Tharsis Bulge's unique geological features and its influence on Martian climate and geology. These missions will seek to map the extensive volcanic structures, providing crucial data on their composition and age. Analyzing the mineralogy will reveal insights into the planet's volcanic history and its evolutionary trajectory. Challenges abound in this endeavor. The vast size of Tharsis, coupled with the rugged terrain, complicates landing and mobility for rovers or landers. Dust storms and temperature fluctuations present additional hurdles, potentially affecting instruments and data collection. The thin atmosphere limits the capacity for traditional aerobraking techniques, necessitating innovative approaches to orbit insertion and surface operations. Objectives extend beyond mere exploration. Understanding the mechanics of the shield volcanoes could offer clues to planetary evolution and the dynamic processes beneath the surface. These missions will also investigate potential volcanic activity in the present day, assessing whether it could contribute to atmospheric changes. Collaboration between international space agencies aims to leverage advanced technologies, ensuring robust data acquisition. Remote sensing instruments will provide high-resolution imagery, while subsurface radar will penetrate the Martian crust, revealing unseen features. The knowledge gained from such missions holds implications not only for Mars, but also for understanding terrestrial planet formation across the solar system. The presence of the Tharsis Bulge plays a significant role in assessing planetary habitability. This region, dominated by an extensive group of shield volcanoes, offers insights into the geological and climatic history of Mars. Volcanic activity influences atmospheric composition, which is essential for sustaining life. The outpouring of gases during eruptions could have contributed to a warmer, thicker atmosphere, potentially allowing liquid water to exist on the surface. Research indicates that the Tharsis volcanoes may have altered the planet's climate over time. Their eruptions would have released carbon dioxide and water vapor, fostering conditions that could support microbial life. Such a scenario raises questions about the potential for habitability in similar regions on other celestial bodies. Understanding these processes becomes vital when exploring exoplanets with volcanic activity, where conditions may mirror those of early Mars. The sheer scale of the Tharsis Bulge also underscores the importance of geological processes in shaping planetary environments. It suggests that substantial volcanic regions can influence planetary evolution, affecting surface and subsurface conditions over millennia. The implications extend beyond Mars, prompting further investigation into the dynamics of terrestrial bodies within diverse environments. This knowledge enriches the ongoing quest to identify habitable worlds beyond our own, marking a significant chapter in planetary science. The Tharsis region presents a compelling target for future Mars exploration missions, spanning approximately 2,500 kilometers across. This vast volcanic province hosts some of the largest volcanoes in the solar system, including Olympus Mons, which towers over the Martian landscape at a height of nearly 25 kilometers. Studying these formations offers insights into the geological history of the planet, revealing how such massive structures influence Martian atmosphere and climate. The potential for discovering subsurface water ice in this region adds another layer of intrigue. Polar caps and permafrost deposits may harbor significant reserves, crucial for sustaining future human exploration or habitation. As missions aim to gather samples from volcanic terrains, they may uncover organic compounds, further informing the search for past life. Robotic landers and rovers will likely prioritize Tharsis due to its geological diversity. High-resolution imaging from orbiters assists in identifying specific sites of interest, focusing on ancient lava flows and caldera structures. These investigations could elucidate the volcanic activity's role in shaping Mars's current environment. Collaboration between international space agencies enhances the prospects of thorough exploration. Each mission contributes vital data, gradually constructing a comprehensive understanding of this unique region and its implications for planetary evolution and the potential for life beyond Earth. The legacy of Tharsis in planetary science transcends its remarkable geological features. This region is a focal point for studying volcanic activity, tectonics, and their roles in shaping planetary bodies. The vast shield volcanoes, towering above the surrounding plains, provide insights into the thermal and mechanical processes that govern planetary crusts. These formations, including Olympus Mons, the tallest volcano in the solar system, challenge existing models of volcanic activity and highlight the differences between terrestrial and Martian geology. The presence of immense lava flows and related structures indicates a history of sustained volcanic activity and potential variations in atmospheric conditions. Evidence suggests that this region has experienced changes in the planet's spin axis, leading to significant shifts in climate over millions of years. Such findings are essential for understanding how volcanic processes can influence a planet's environment, potentially impacting habitability. Geophysical studies, utilizing data obtained from orbiters and landers, have revealed the complexities of Tharsis's interior structure. Gravitational and magnetic measurements indicate a dynamic history characterized by variations in magma movement and crustal formation. Insights gleaned from this region extend beyond Mars, offering comparative perspectives on volcanic activity across the solar system. They illuminate the interactions between geological processes and atmospheric evolution, enriching our understanding of planetary development as a whole. Current exploration of the Tharsis Bulge reveals a complex interplay of volcanic activity and tectonic evolution. This region hosts the largest volcanoes in the solar system, including Olympus Mons, which rises to heights nearly 3 times that of Mount Everest. Geological surveys indicate that these volcanoes have been active over billions of years, with lava flows and ash deposits revealing a history of eruptions that shaped the Martian surface. Recent studies focus on the potential for volcanic outgassing to have influenced Mars's ancient atmosphere. The release of gases like water vapor and carbon dioxide may have contributed to a more hospitable climate, allowing for the possibility of liquid water. This hypothesis is supported by findings of ancient river valleys and lake beds scattered across the Martian landscape. Future research aims to utilize advanced satellite imaging and robotic landers to further investigate these features. Understanding the stratigraphy and composition of volcanic materials will provide insights into the thermal and chemical evolution of Mars. Additionally, examining the impact of Tharsis on the planet's axial tilt and rotation may reveal broader implications for the stability of terrestrial planets. Continued analysis of this region not only aids in deciphering Mars's geologic past, but also enhances knowledge of planetary processes applicable across the solar system. This exploration remains a pivotal aspect of astrobiological and atmospheric studies. The Tharsis Bulge represents a striking feature in the study of planetary evolution. This region, characterized by its colossal shield volcanoes, offers insights into the geological processes that shape planetary bodies. The sheer scale of these formations, including Olympus Mons, the largest volcano in the solar system, underscores the potential for volcanic activity to influence a planet's surface and atmosphere. The presence of such immense structures raises questions regarding the thermal history of Mars and its ability to support dynamic geological processes. Investigations into the Tharsis Bulge reveal its impact on the planet's rotational dynamics. Variations in mass distribution due to volcanic activity can alter a planet's spin axis, affecting climate patterns and atmospheric circulation. This relationship highlights the interconnectedness of geological and atmospheric phenomena, suggesting that significant volcanic activity can create feedback loops that further influence environmental conditions. In addition to its geological significance, this region serves as a natural laboratory for understanding the evolution of planetary atmospheres. By studying the remnants of ancient lava flows and the potential for past water activity, researchers can draw parallels with Earth's own geological history. The Tharsis Bulge not only enriches our comprehension of Martian history, but also informs broader theories regarding planetary formation and evolution across the solar system, enhancing our grasp of the factors that govern planetary systems.